Hi folks, I'm going to try and talk you through collision theory and reaction mechanisms. If you go into the heat and rates unit, there's a handout on reaction mechanisms that I want you to try and complete. Now, collision theory tells us that a chemical reaction won't take place unless the chemicals have proper force when they collide and they have the proper orientation. So if we have two molecules in a beaker, remember you've got billions and billions of molecules when you're doing a chemical reaction, even more than billions and billions, even more than trillions and trillions, that very few of these collisions to make the chemical reaction occur are successful, because if they don't have enough force and if they're not facing in the right direction, then you will not have a successful reaction. Now, if you get 1 out of every 1 trillion molecules colliding, the reaction is going to occur. You've got to keep in mind that we have many molecules in this container, and we only need a few of them to collide with proper force and orientation for a reaction to occur. Sometimes this is hard to imagine. Something called a Maxwell-Boltzmann distribution curve will show the number of successful collisions for a reaction to occur. When you go in and start the assignment for today, there's a video link in there talking about CFCs and reaction mechanisms. A reaction mechanism is all the small steps that add up to give the overall reaction. So make sure you watch this video after you do question 1 on the assignment today. An example of a reaction mechanism, this will be for the biologists, would be photosynthesis. We write the overall reaction. So the overall reaction is 6CO2 plus 6H2O gives 1 glucose, C6H12O6 plus 6O2. But this happens in many complicated steps called the light reactions in the Calvin cycle. So often the overall reactions that we see in chemistry are made up of smaller steps that last millionths of a second. When doing the assignment today, please skip questions 6 and 7. Skip questions 6 and 7. Just as a reminder, you're responsible to know what collision theory is, and that is that to have a proper chemical reaction, 2 molecules must undergo proper force and orientation before the collisions that occur must occur with proper force and orientation of the reactants before a reaction can take place. And because you have many molecules in a reaction, you only need some of these to have a proper collision for a reaction to take place. Okay, this is your worksheet for the day. I'm going to go over a few concepts here. This is your overall reaction. So a chemist would write down CFCl3 gives you CFCl2 plus Cl. And what this is the chlorofluorocarbons that leak out of old refrigerators that get up into our upper atmosphere. And what happens is one of the chlorines is cleaved off by radiation, and this causes a chain effect that breaks down ozone, which we don't want our ozone layer breaking down. These are the elementary steps or smaller steps that make up this overall step. 2 things are important here. One is to realize a catalyst when you see one. A catalyst will be in the very first line on the reactant side, product side, and will also appear on the very last line in the product side. In other words, this chlorine started in the reaction. When the reaction was done, it was still there. So the definition of a catalyst is a substance which makes a reaction go more smoothly, that was already undergo this reaction, and it's not used up. So it's there at the beginning and it's there at the end. So this is our catalyst. Another thing that's important to note is an intermediate. An intermediate is something that is made somewhere in the reaction. So this is made, it's produced on the product side, and then it's used up somewhere else in the reaction. So that's an intermediate. You will usually only have one catalyst in a reaction, but you can have many intermediates. Explain how a small amount of chlorofluorocarbons can destroy a large amount of ozone. You'll have to watch the video for that one, but it's because it acts like a catalyst. You need very little catalyst because a catalyst can be used over and over and over again. E is not an important question. It says what breaks down the bonds of CFCl3 and releases the free Cl atoms, and that's just radiation, UV radiation. What you're also going to notice in some of these reactions is they'll say slow or fast. These are the rate determining steps, the slow ones. You can speed up the fast one as much as you want, but it won't speed up the reaction. You have to speed up the slow reaction if you want to speed the reaction up. So a scientist or a chemist would speed up the slow reaction using a catalyst. So if you see two people getting ready to go out at night, and the one person gets done very quickly getting ready to go out, and the other person takes a long time, if you speed up this person who gets ready right away, it does not speed up the reaction at all. You've got to speed up the person who's not getting ready quickly. So now they want you to graph a potential energy graph. So I'm going to give you some basics on that. In a potential energy graph, what you do is you figure out whether it's exothermic or endothermic. Exothermic means energy out, so that means your reactants are going to have more energy than your products because the energy has left. These are often qualitative graphs with no numbers on them, so this would be like time, progressive reaction, potential energy here, oops, energy potential, and we know from this previous page that this reaction had two parts to it to make up the overall. Oh, let's do the overall up here. So I'm going to go backwards for a second. To get the overall reaction, we've got O3 plus O. We take out our catalyst and we take out our intermediate. On the other side, we've got 2O2. You can cancel out going across from products to reactants, or you can add up if you're on the same side of the reaction. Notice it balances. 4 O's on this side, 4 O's on this side. That's the overall reaction. Often the catalyst is written up above the arrow, showing that it's not used up in the reaction, and we don't write down the intermediates. Anyways, back to the graph. There were two parts to this graph, so there were two elementary steps. One was slow, one was fast. So what happens is every time you have a step, you have a bump. The bump of the slow step is higher than the bump of the fast step. So there's the slow step. This is higher. That means it took more energy to get that slow step to occur. The fast step is going to be lower. So this is our potential energy graph. Now, if you add a catalyst in, what a catalyst does is it lowers the activation energy. So it makes this reaction occur more easily. So for any reaction, you have to put, well, not for all reactions, but for a lot of reactions, you have to put activation energy in to get something started. So if you were smoking a cigarette, that activation energy would be the heat from the lighter. So you've got to put activation energy in, energy of activation, to make that first reaction occur. Then the second reaction was a fast one, it needs less energy. Overall, the products have less energy than the reactants. You are to skip questions 6 and 7. I'm trying to see if there's anything else in here which would stop you from being able to complete this. You should be able to get through page 4, no problems. Sorry folks, I didn't have these in the right order. Give me 1 second here. You have all the information you need to get through these. Some of the questions are going to be tougher as you go along. So in this activity, the information is built up. Use your problem solving skills to try and get through this. You should be able to get through pages 5, 6, 7, and 8. You should have the information you need to get through. Question 14 is a very tough one. I'll probably make a separate video up taking up question 14. By all means, if you have problems with a question, fire me an email and I will make up a video showing you how to do things, but I will definitely make a second video up for 14.